The next speaker, Keith Black, once again, 3 or 4 years ago, at Teddy came and talked, and Joe Sachs was in the audience. Come on up, Keith. Joe Sachs was in the audience, and Joe had given a remarkable talk about 5 years ago on ER. He was the doctor who checked all the scripts, and then he also directed some shows and was a professional advisor for some shows. And then he got men. Who's the guy who's the actor from? Noel. What's his last? Noah Wiley, some young kid. He came to a few of the meetings, and then I even had a walk-on on ER. I'm sure they told you all about that, but I was Dr. Aiken, and I walked across, and then another scene I walked back was the 100th show. Anyway, I think Joe was so taken with Keith that he wrote a whole story around you, and it ran on ER. So, fresh from that fame, and whatever, Keith Black.
Thank you. Well, thank you, Richard, and it's great to be at any TED conference, one of the best conferences that I could ever attend. But I think that actually I have probably one of the best jobs on the planet in that I work with probably the most incredible structure in the universe, the human brain. And, they say that if you want to understand an artist, you study his art. If you want to understand God, you study nature. And science is the study of nature, so the ultimate goal of science is to understand God. And when I look and I work with the most incredible structure on the universe, it brings me closer to probably the most supreme force within the universe, and that is the human brain. So I've done about 3,000 operations to remove brain tumors. And the challenge that we have when we open the skull is essentially this right here, is how do you actually remove a tumor from the human brain and leave all of the eloquent structures around that tumor intact. So what we're looking at is the skull has actually been opened, and you see the membrane that protects the brain, the dura mater, which is Latin, as you all know, for tough mother, has been removed. And within this area that you see here, which is the left hemisphere, is areas that control language function, areas that control motor function. We actually have this strip electrode out here actually mapping out the motor cortex. This patient is awake. The brain has no sensation. So if you need to map out language, which we had to do here, we could do that. And the problem is that you see the tumor here. It's not very clear. We don't have a very well-defined margin. So you can see the tumor in the left temporal lobe, and we can do all kinds of things like functional MRI scans, and for a lot of these people, we can get the tumor out. This is bouncing around quite a bit. So, and you can see the tumor has been removed, but unfortunately, a lot of these tumors are not benign. They're malignant, and so they recur. And what I'm going to do is, since this is bouncing, I'm going to have you actually do this for me. So let's advance, advance, advance. So what I've focused on is to essentially to work within the laboratory to design technologies to try to develop an effective strategy to treat brain tumors. And the technologies, let's go back one, the technologies that we've looked at are technologies to open the blood-brain barrier, non-invasive ways to destroy tumors using microwave radiation. We've developed a cancer vaccine that's based on dendritic cells that you heard some about earlier. We're beginning to try to explore the possibilities of using stem cells to treat tumors and also to identify new molecular targets. If you look at the blood-brain barrier, capillaries within the brain are different than capillaries anyplace else in the body, in that they essentially form a barrier that do not allow most compounds to cross out of the blood into the brain tissue. And this is very important under normal circumstances because it protects the brain from toxic compounds. The lunch that you just had, if the barrier wasn't in place, we would all probably be convulsing now and be in coma. But the brain also needs to sort of get nutrients, and so even the main energy source of the brain, glucose, cannot cross these capillaries. Glucose has to be taken across by a special transport carrier, a glucose transporter. And so the only compounds that can actually get across are these very small lipid-soluble compounds that can diffuse across the membrane. So essentially 98% of compounds that can have a therapeutic effect within the central nervous system cannot get across the barrier to treat a variety of diseases from depression to brain tumors. And one of the things that is always puzzling to me is that none of the major pharmaceutical companies have a program in brain drug delivery to really address this concept. And there's a misconception that the barrier is sort of disrupted in brain tumors so that the chemotherapeutic compounds can get across. That's not true. So what we've tried to do is to develop a technology that could increase drug delivery selectively into brain tumors without increasing their delivery into normal capillaries. And we've been able to do that by exploiting biological differences that we've been able to identify between tumor capillaries and normal brain capillaries. And a picture is worth 1,000 words. So what you see here is a coronal histological slice of a rat brain with the tumor, and we've injected in a radioactive tracer, carbon-14 labeled dextran, into the vascular system. And you can see that none of the dextran gets into the normal brain because of the blood-brain barrier. You see a little bit of it gets into the tumor, but not very much. This is why you would see enhancement on an MRI scan or a CT scan with the tumor if you gave a contrast agent. And you can see most of it is just still localized within the large vessels on the surface of the brain. But using our technology to essentially modulate the blood-brain barrier, you now see a second animal with the tumor in it, and now you see the tumor essentially stands out like a light bulb. We've been able to increase delivery of chemotherapy within these tumors by up to 1,000%. And even the finger-like projections you can see even stand out here, and even a small cluster of tumor cells located on the surface of the brain, we could even increase delivery of these compounds to. Now you have to remember that the distance between here to here is less than 2 millimeters. This is below the resolution that you would see on an MRI scan or a CT scan. So even small microscopic areas we can even increase delivery to. Next slide. And we've been able to do this in man. This is a PET scan where you can see a patient with the tumor in the right temporal lobe, sort of before treatment and now after treatment, dramatically increasing delivery of these compounds selectively to the tumors. That was actually featured on the cover of the Journal of Neurosurgery. Next slide. And in an early study, in an early phase 1 study, where we had 4 patients with the most aggressive type of brain tumor called a glioblastoma multiforme that had failed radiation, surgery, other types of treatment that had essentially about 2 or 3 months to live. When we gave this compound in combination with chemotherapy, you could see that essentially 4 out of 6 patients had a response. So this is the scan before treatment and after treatment, and before and after, and before and after, and then the other patient had one before and after. Next slide. And we've now actually gone on to sort of refine the sort of pathway even more, and we've now identified particular channels that have a very potent effect on selectively opening up delivery of these chemotherapeutic compounds within diseased tissue, areas of stroke and areas of tumors selectively without increasing delivery into normal brain areas. That was actually featured, I think, last year on the cover of Pharmacology, Experimental Pharmacology. Next slide. And so what is the need? I mean, we know, for example, that most patients with lung tumors and about 30% of patients with breast tumors, melanoma, colon cancer would ultimately have spread of the tumor into the brain. And if you look, for example, at lung cancer, about 60% of patients with lung cancer will have spread of the tumor to the brain within 2 years. Now, about 70% of the tumors will respond if the tumor is outside of the brain, but once the tumor spreads to the brain, it's protected behind the blood-brain barrier. So there's only about a 10% response rate to tumors from the lung that spread to the brain, unlike a 70% response to tumors outside of the brain. And so our technology will actually increase delivery of drugs to these tumors that are within the brain and hopefully allow chemotherapy to be more effective. Next slide. I don't know how many of you were actually Star Trek fans when it was sort of on. But when I was growing up, I was a Star Trek fan, and there was an episode of Star Trek where the Enterprise had to come back to the 20th century and get a well to sort of take to the future, and Bones went into an operating room. Do any of you guys remember that program? And and so Bones was in the 20th century operating room, and he turned to Captain Kirk and said, "My God, Jim, they're actually cutting the patient open." And one of the things that I've always wanted to do was to eliminate the need to do what I do, which is brain surgery. Next slide. And so we developed sort of a technology to essentially use microwaves to destroy brain tumors without the need for surgery. And actually, we asked a question whether that might be better than actually cutting the tumor out, just leaving those dead cells in place. Next slide. So I was riding on the airplane, and I saw this ad, and it said one of these women had back surgery yesterday, and you can see the little small Band-Aid on her back right here. Next slide. And so our response to that ad was that one of these people had brain surgery 5 minutes ago. And you can sort of see the first patient that we treated with microwave ablation. Next slide. So we developed this little device that can focus microwave energy right on the brain tumor. You can do this right in an MRI scan. So the patient can come into the MRI scan, get diagnosed with a brain tumor, the tumor can be destroyed, and they can go home the same day. Next slide. So thank you. So here's one of the patients that we treated. This was actually a very interesting patient because she had multiple personality disorders and about 4 or 5 different personalities. And she had a tumor in the left frontal area, which is very close to language areas. And so we had to do the surgery awake, which is actually quite amazing because you don't know which personality is going to come out in the operating room when you wake her up. And unfortunately, we mapped out part of the tumor right into Broca's area, which is one of the language areas, and we could not remove all of the tumor. And we treated her with radiation and with chemotherapy, and amazingly, the tumor responded for about 4 years, but it came back. And you can see our previous resection cavity here, and you can see tumor here and tumor here. And so we did a microwave ablation, and we destroyed this right in the MRI scanner with the microwave ablation. And we had to leave this tumor here behind because it was right in the language areas. And amazingly, 32 weeks later, both areas had regression of tumor. So it really asked the question of whether or not it may actually be better to sort of leave all of this necrotic debris in place because that gets mopped up by immune cells that actually come in to remove that necrotic debris and take that back to lymph nodes, which may actually stimulate an immune response against tumor that remain elsewhere. Next slide. So then we went on and said, well, you know, the body, God gave us the immune system, which is actually the most potent way of fighting any sort of disease that we have. And we asked the question, can we develop a vaccine to stimulate the body's immune system against the tumor? And would these vaccines be safe, or would we actually generate an autoimmune response against normal brain tissue, convert a brain tumor into MS? And if we didn't do that, would it be possible to actually get the immune system to be able to recognize these immune cells? And if we could recognize the immune cells, would we actually increase survival in these patients? And we published our first phase 1 trial in cancer research in 2001. Next slide. And if you sit down and you think about what would be the ideal treatment for brain cancer, we know that the treatment needs to be able to reach the entire volume of the brain because cancer, by definition, is diffuse. It's not localized. It should not be toxic to normal brain cells because the brain is sacred. No one wants to lose any normal neurons. And it should retain the ability to kill tumor cells for a long duration because if the cancer comes back, we want the immune system to be able to sort of recognize it and knock those cells out. Next slide. So the nice thing about a brain cancer vaccine is that it meets all of those criteria potentially. An activated T cell can actually cross the blood-brain barrier and get anywhere into the brain that there is a vascular supply. The immune system is very precise. Okay, so it can knock out the tumor and leave the normal cell intact. And the nice thing about using immune cells is that they can retain memory. Next slide. And if you think about what happens in tumor immunology, and you look at this like waging a war, And you say, well, what is the cancer doing to essentially avoid an immune response? Why do brain tumors not generate an immune response naturally? Well, the first thing that a brain tumor does, first thing most cancer do, is that they make themselves invisible to the immune system. They downregulate MHC antigens, they lose B7, they lose all kinds of molecules on their surface that would allow them to be recognized by the immune cells. So one theory is that we're developing cancer all the time, and our body is able to recognize it and knock it out, but if the cancer is going to survive, it first has to become invisible to the immune system. Second, the cancer that we found in our laboratory is actually decreasing the number of naive T cells that the immune system can actually call up to fight the cancer. It's also actively trying to suppress an immune response. The cancer is actually releasing TGF-beta, a number of immunosuppressive cytokines, to try to block an immune response, and it actively kills tumor cells that can invade into the tumor, potentially through FADs and FADs ligand, inducing apoptosis. So you would have to think that if the cancer is putting that much energy to avoid an immune response, it must have a great fear of the immune system. So why not attack the defense? Why not activate an immune response to try to counter what a cancer, which is very efficient, it's like a shark, it doesn't waste a lot of energy, is using to try to avoid attack. Next slide. So we've now performed a number of trials. We have a phase 2 trial currently using dendritic cells for patients with malignant brain tumor. And we've completed 3 phase 1 trials. And since 1998, we've treated more than 50 patients with the dendritic cell-based vaccine. Next slide. And this is actually the first patient that we treated, which is still alive and doing very well, despite having a malignant cancer with about 9 months of predicted survival at the time that we gave her vaccine in 1998. You can imagine that for us, used to doing sort of very big operations, everybody sitting around waiting till she first got the vaccine, waiting for something to happen. The little shot was sort of anticlimactic for us, the surgeons, just sitting there waiting. But it's essentially just getting a shot. There's 3 vaccines separated by 2 weeks. We isolate dendritic cells from the blood. We remove the tumor, strip the tumor antigens from the tumor, and actually pulse those with the dendritic cells using a variety of methodologies and give those back to the patient after the shot. Next slide. And we were very encouraged to find that after vaccination, about 60% of the patients actually had T cells that could recognize their tumor based on a variety of assays, such as CTL assay. And for a number of patients that had to go back for a reoperation, we found that before the vaccine, if this is a histological section of a GBM, almost none of the tumors had an infiltration of immune cells. But after the vaccine, about 50% of the patients had infiltration within the areas of tumor of CD8, which are activated T cells, as well as CD45RO, which are memory T cells infiltrating into the tumor. Next slide. And what we could actually see, and I just roll through this a few clicks. Next, you could actually see, this is sort of a cartoon of what we now believe is happening of the immune cells, next, actually knocking out tumor cells that are sensitive to the, click it one more time, that are actually sensitive to the T cells, leaving the red cells behind, which are resistant, so that you end up, after immune modification, next slide, of these cells, next, one more time, cells that are no longer immune sensitive, but are now immune resistant. Next slide. And what we found is that the cells that remain after selective immune pressure on these tumors have genetic and molecular differences from the cells that were present before the tumor that now make them more sensitive to other therapies. And what we're finding is that the combination of therapies is actually resulting in sort of this very long tail of survival for patients with glioblastoma that is almost universally fatal at about 2 years. Less than 5% of patients with GBM will survive less than 2 years. With this combination approach, we're seeing about 30% of patients alive now at 3 or 4 years. So that's a significant improvement. Next slide. And when we look at our Kaplan-Meier curve, this is sort of the historical survival of patients without the vaccine. And this is in one of our phase 1 studies that was actually published in Cancer Research. We increased the median survival from 24 to 94 weeks. Next slide. So our research efforts now are actually trying to identify subgroup of patients that may most benefit from the vaccine. We believe that we can identify patients that have a large number of naive T cells that can be activated by the vaccine that appear to actually do even better, to try to increase this pool of sort of naive T cells to be recruited into the fight against the tumor. We're looking at strategies to try to decrease the ability of the tumor to suppress the immune system and induce apoptosis of tumors that infiltrate immune cells that infiltrate into the tumor, looking at synergistic treatments, and actually trying to avoid the work of making and customizing the vaccine for each patient, looking at the ability of actually just using a microwave ablation, creating this necrotic debris, and putting the dendritic cells right into the tumor to activate an immune response in patients. Next slide. We all know about gene array technology. This actually just looks at a gene array between normal brain and normal corpus callosum, and each one of these dots represents a different gene. When you look at GBM compared to normal brain, what we found is that about 2,000 genes overexpressed, about 700 genes that are underexpressed. Next slide. But we can pick out certain genes, and we identified laminin 8 as being sort of a novel gene that appears to allow tumor cells to invade into their neighbors, and we can block that ability with antisense technology, preventing invasion that we were able to identify using these array profiles. Next slide. Stem cells, we've been able now to actually harvest right from the bone marrow in adult rats, and we're looking to actually harvest neural stem cells from adult patients. And what we've demonstrated is that these neural stem cells that we've been able to harvest, actually when you put them into the brain, they actually track right to tumor cells. They can go right across the midline and track right to the tumors, like a heat-seeking missile seeking the heat of a jet engine. And one of the problems with tumors is to identify that microscopic infiltration. And we've been able to genetically engineer, next slide, these stem cells with things that can light up the immune system, such as IL-12, put them into the brain, they go to the tumor, and we can enhance the immune response with neural stem cells and increase survival in mice. So you can imagine the combination of lighting up the tumor with these neural stem cells. They're sort of like the special ops, lighting up where the cruise missiles come to once we give a vaccine systemically with the dendritic cells in this sort of fight to actually try to knock out this cancer. Next slide. And this is just showing these neural stem cells that have been harvested from the bone marrow in the adult rat, actually tracking right to isolated little pockets of tumor. Next slide. So how do we outsmart brain cancer? This is how I would envision hopefully treating patients with brain cancer in the next few years. Not doing surgery, but just doing a little biopsy and doing a microwave ablation right in the MRI scan, inserting dendritic cells right at that same time in the MRI scan into the necrotic tumor. Also inserting stem cells that have been genetically modified to track out to isolated tumor cells that can be sort of identified for the immune attack, increasing the number of naive T cells that can be recruited in the fight against these tumors, identifying new molecular targets, and opening up the blood-tumor barrier for delivery of some of these novel compounds that are also being developed. Next slide. And basically putting myself out of a job and going to the beach. Thank you.